Hello. Okay, I think everything's set up. Let me see. Can you hear me?
Yes, Professor.
Okay, thanks. All right. And okay, so what we're going to do today is go through more detail of language 7. Okay, so look, we talked a lot the other day about functions. We've talked about this stuff about function definitions and function calls. Okay, and let's see. Last time we talked about, again, function definition, function call. Okay, we looked at the last week we mostly emphasized the syntax for function definition, and function call. Remember we needed this apply to make it a tree, to create a proper tree structure. Oh, actually, I wanted to show you another reason why we use the apply. Let me show you real quick. Let's go back over that. We want our language is a language of trees, so we need things to be trees. Okay. So we need the language to have trees. Okay. Now, naively, you might say f of, so I have a function f, and I want parameters x, y, and z. Okay. Well, that sure looks like a tree. I can write that as f, x, y, z. Okay. And then, sure, that's a tree. F is the root, and then it's got branches x, y, and z, and it sure looks fine. Why not just let that be the syntax? Okay. Why not just have that be the syntax? And the argument I gave you last week for not using this syntax was a function of 0 arguments, a function f with no arguments. Okay, f with no arguments. If you turn that into a tree, it looks like f like this, which is what's actually done in Lisp. But then that's not a tree. That doesn't fit the grammar of our tree, because our grammar for a tree with one root is f. But then we don't have a sense that that's a function call. It just looks like a variable. So this is a function with no parameters. Okay. This is the Lisp notation. But as a tree, it looks like a variable, not a function. Okay, so you think that this would be a variable and not a function. Okay, that's one reason for you. Now, if you turn that into the apply notation, you would write, okay, the first one would be apply f to x, y, z. Okay, that's a tree. And then the no argument one would be apply f. Okay, that's still a tree. Okay, both of these are trees. Okay, but here's even a better reason. Like if I wanted to, I could make this work. Okay, what I would do is every time you look up a variable, you'd have to ask, is the variable a function value or is the variable a number value? If the variable is a number value, return the number. If the variable is a function value, call it with no arguments. Okay, so with some playing around with the interpreter, I could make this notation work even for the no argument case. But you wouldn't use this notation for a function with no arguments. You'd use this, and then you'd have to be then you'd have to rewrite the interpreter. But here's even a better reason to use the apply notation. Okay. What if I want to do something funny? Okay, you don't do this in C, but yeah, you could, but you usually don't do it. Look at something like this. I have two functions. Suppose I have a function f of x is, say, x squared, and I have a function g of x is x cubed. Okay. Now I want to play a funny game. I want to write the following expression. Y equals if Boolean, I'll just say if B, then f of x else y, f of x else g of x. Okay. Okay. I want a Boolean, and if the Boolean is true, I want to call f. If the Boolean is false, I want to call g. Okay. Okay. Now, this can be rewritten in a really elegant way if I think about this way. Okay. Instead of saying y is the result of calling f or the result of calling g, let me write this. H equals if b, then f else g. Now notice now h is not the result of calling the function, it is the function. So then if I say h of 4, I'm calling either f or g, depending on what the Boolean is, okay? Or if I call h of x, okay? So here I'm doing, this is, you can do this in any language. If Boolean, then call f, else call g. So y is the result of calling either f or g. This is a little bit more abstract. Here I'm saying that h is either the f function or the g function, okay? And the result of h is either one of those two functions, and I call the result, okay? So these two lines together pretty much do the same thing this does, okay? Now I can do something really weird. And you can do this in a few languages, okay? Compress these two together and do the following. It looks like something like this. If B, then F, else G, that's a function. It returns either F or G, and apply it to X. Okay? In almost all functional programming languages, you can do this. Okay? And you can actually even do this in C using function pointers. You can even do this in C. You can write this in C as something like B question mark F or G, where those are function pointers X. Okay. You can, yeah, it'll work. If you've got F and G defined as function pointers, you can write a Boolean to choose either that function pointer or that function pointer and call that function on that function pointer. Okay. Now, let's turn this into our language, our tree language. Okay. If we turn that into our tree language, it looks like the following. Okay. The if expression looks like this. If B, F, G. There's the if. Okay. And then that's the function we want to apply to X. Okay. Now, if we used Lisp notation, it would look like this. Okay. This is Lisp notation. That's not a tree. Okay. Yeah. Not even close to being a tree. Okay. Because look, in the root position is a parenthesized expression. Remember, a tree, the syntax for tree is a root, then a tree, then a tree. You know, and as many of the, you know, a root and then one or more trees. Okay, So the syntax for a tree is a root, which is just a symbol, and then one or more trees. This has got, in the root position, a tree. So it's got a tree. This is actually the syntax for what I just wrote up there is tree, then another tree. It's actually, yeah, it's got a tree, then another tree. That's called an S expression. This syntax has got a name. It's called an S expression. And Lisp is not a tree language. It's the language of S expressions. And you can look up S expressions. There's a Wikipedia page about them. Okay. S stands for symbolic. They're symbolic expressions. They were designed for the Lisp language. They're one step more sophisticated than tree language. Okay. S expression, our language is a tree language. Lisp is actually, so this is an S expression. It's not really a tree, it's an S expression. Okay. This is a tree. If you want a one node tree, you write it like this. This is a one node S expression. Okay, this is C in Java notation. This is Lisp notation. This is R notation. Okay. Over here, we would have a real hard time turning this into anything like something our language can handle. But what we do is then say, apply the result of the Boolean F, B, F, G to the operand X. Okay, that's our notation. This is now a real tree. Okay, the root is apply. The first branch is the result of computing a function. So that branch is the function. Instead of it being a function name, it's an expression that evaluates to a function. So it's something that evaluates to a function. And then there's the operand. Okay, okay. So apply something that evaluates to a function to an argument. Okay, without the apply, you don't have a tree, you have an S expression. And I wanted to avoid the language of S expressions. They're one step more complicated than trees. They're not as complicated as C style syntax. You know, it's less complicated than C style syntax, but it's more complicated than tree syntax. To be able to do this kind of trick here of saying apply the result of an expression, which gives you a function, to an argument, then I had to use, that's what the apply syntax is really there for. It's so that we can, now if we go to if we look at the syntax of language 7, if you read the syntax carefully, it explains that the apply, this expression here is supposed to be something that evaluates to a function. The simplest case is just the name of a function, but the language actually allows this to be any expression that evaluates to a function. So it allows things like this guy here, apply this funny little Boolean that says, if B is true, give me back the function F, otherwise give me back the function G. Then whichever function you get back, apply it to X. Okay. Now, in language 7, there's a whole bunch. If you look in the language 7 examples, there's a whole bunch of examples like that. See if I find one. Maybe, let's see. Oh, here it is. It's right there. Here's a function that returns. Okay, here I've written. Here I said, here's a function F. Here's a function G. Here's the H that's either F or G. So that's this note. That was. Oh, I'm sorry. That was this example here. There's some function f and some function g, but it's this example here. There's a function f and a function g, and then h is either f or g. Then you want to call h of x, okay? And so that example is written here. Define f, define g, h is either f or g, and then you can call h. But then it can be written more abstractly. Let's see, where's the more abstractly written? You could put the if statement right after the apply. So let me see if I can find, here's the, no. I thought I had an example where it was like this one, where the if comes right after the apply. See, maybe it's in one of the other, let's see if it's in number 3. Yeah, there it is. Apply the result of that if. See there, if B, F or G. So there it is. Apply the result of the Boolean expression to 5. Okay, notice it's pretty abstract. Okay, so there's the function f's definition. There's the function's g's definition. See, x squared, x cubed. Here's a Boolean that's just set to be true. Apply the result of this expression to the number 5. You can do this in C. You can't do this in Java very easily. I'm not sure. You might be able to do this in Java. Probably you can, but it's going to look really ugly. In C, you can do it by letting f and g be function pointers. Okay, so you could have f is, in fact, actually, you don't even, I mean, every function name is by definition a function pointer. So you could basically just do this with a Boolean and the names of 2 functions. And if you use the right syntax, then you could call the result of the Boolean immediately on a variable of 5. Yeah, and I think the C syntax would be, I think it would look like that. I think you could do it like that. I think that would work. If f and g are the names of the functions, yeah, somebody could try it, but I think it'll work just like that. Okay, that would choose that function pointer or that function pointer, and this is the notation for calling the function with that argument. Okay, Java would probably end up looking, so in C, I think you could write it pretty much exactly like that. I think in Java, it would end up being kind of messier, because in Java, functions don't live on their own. Functions are always wrapped inside of objects. So you can't just have a function name. Yeah, and so you have, and then you can't put the name. You can't put here a static. You can't put a static function there or an object function there. You have to do something kind of tricky. I'm pretty sure you can do it in Java, but I think you have to jump through hoops to get it to work. Okay, and the problem is that functions don't live by themselves. Functions live only nested inside of objects and classes. Static functions live in classes. Instance methods live inside of objects. So every function is either sitting inside of an object or if it's sitting inside of a class. And that makes this idea messy in Java. Okay, but not in C, it works pretty well. In our language, it looks like this. But see, that's what we need the apply for. Without the apply, we'd have this syntax, which is valid Lisp. Okay, but it's what's called an S expression, not a tree expression. Okay, so we want tree expressions. Okay, S expressions are just one step more complicated than tree expressions. The Lisp people wanted S expressions because they're more elegant. They didn't want to have to type apply every time you call a function. So they let you they let you have parentheses like that. So you can say things, you can have an expression here that returns a function and then passes it arguments like 3 or 4. Okay, so this could be an expression that evaluates to a function. Okay, so it can be an if, it can be almost anything you want. You could, as long as this thing, as long as this expression returns a function, then that function gets called. The left parentheses essentially becomes call that, okay, with those parameters. So in a nest expression, you read left parentheses as call. So if somebody writes this, that means call A with parameters B and C, okay? And if somebody writes this, as an S expression, that means call this guy, whatever he is. Well, what is that guy? You get him by calling A with parameter B. When you call A with parameter B, you better get back a function because you're going to call it. If you call A and get back, if you call A with parameter B and get back a number, this thing will fail at runtime because you can't call a number. So, but this is call that thing. That thing is call A with parameter B. And that better return a function because you're going to call that function with parameters C and D. And then you can nest this all you want. You could then do that's an S expression. Okay. You're calling that thing. Well, what is that thing? Well, that thing is a function. How do you get it? You get it by calling that thing with parameter C. Well, what's that thing? It better be a function. Where does it come from? You get it by calling A with parameter B. So you call A with parameter B, it gives you back a function. You call that function with C, it gives you back another function. Then you call that function with parameters D and E, and you get back your final result. Okay? So left parentheses is read as call. Call the first thing in the list. You know, call the first thing in the list. Call A in this case. Okay, that's the language of S expressions. So it's a little bit trickier a language. You can't write this thing as a tree. You can't write this as a tree. Okay, it's written in a different way. It's not thought of as a tree anymore. It's this thing called an S expression. Okay, now in our language, we can make sense of that one. We write it this way. Apply this guy to D and E. But what's that guy? That's the apply of this guy to C. And that is the apply of A to B. Okay, so apply A to B, you get back a function. That function gets applied to C, then you get back another function. Then that function is applied to D and E. Okay, and you get more. It's more verbose. That's more verbose than that. Okay, and this one in our language would be written as apply A to B and C. Okay, so S expression, tree expression. Okay, turn it into a tree by using the keyword apply to turn it into a tree. Okay, remember, actually, that is now in this case, that one is a tree. That particular S expression happens to be a tree, okay, where A is at the root. Okay, so that particular S expression is a tree. Here, that one happens to be a tree. Okay, but we would write it, it's still read as apply A to parameters B and C. When you get to this kind of S expression, it's no longer a tree. See, this one's way more complicated. It is not a tree, okay? But if you unravel it our way, apply, 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 there's three parentheses in a row mean there's three function calls. Yeah, that's the outer function of an inner function of an inner function, okay? Okay, so there's three function calls there, okay? So that's the real reason that we're using the apply notation. Initially, I said it was because of these zero argument functions. A zero argument function, that's one good reason to use the apply notation, but it's not the best reason. Because if we were only worried about zero argument functions, I could probably solve the problem without, and still keep the tree structure. Yeah, I could keep the tree structure in the interpreter and not need the apply if all I was worried about was zero argument functions. But what I really want is this more modern notation that you could have an expression that returns a function, okay? Expressions that return a function, and then you have to call the result of the expression that returned a function, okay? So like, and see, it's not an especially sophisticated thing, being able to call the result of an expression. Having an expression return a function can be done in C. Okay, it's not considered all that deep a thing to do. Okay, it's just Java. Java makes it hard because because it's object oriented. But in C, it's not object oriented. So C makes it pretty straightforward. You just say use that function name or that function name. You think of it as you're going to call a function, and it just lets you choose which function name to use, F or G. Okay. But turning that into a tree is tricky. Yeah. To turn that into a tree, if you just do it naively, you end up with S expressions, which is fine for the list people, but not for us. We don't want to parse S expressions, so we want to stick to parsing trees, so the apply comes in. Okay. All right. Okay. Now, the other thing we did last week was this was the syntax of function calls, and then the other thing was the syntax of function applications. I'm sorry, function calls and function applications are the same thing. The syntax of function, the other one was the syntax of function definitions. Okay, the other in class the other day, we did function def applications and function definitions. Okay, yeah, and this was the definition of function. This was the syntax for function definitions. Okay, and remember the idea we introduced here was separating function. Now, one thing I want to point out, we're really doing pretty sophisticated stuff mixed into this. What we just mentioned, what we just talked about a minute ago, this difference between S expressions and trees, the deep idea is not S expression versus tree. The deep idea is that you could compute an expression to get a function result. That's the interesting idea, that the result, that the thing to call is not just F. The thing to call is, oh, do this calculation, which gives you back the function that should be called. That's the really deep idea here. And we need the apply notation to make that deep idea work. But the deep idea is that what I call, or if I think here in the syntax, what do I apply? The result of that expression to those arguments. And there's no reason to think that that thing is just a variable. That's not going to just be a function name. In the programming you're used to, you call F or G or H. But now we want to get to thinking more abstractly. You call the result of some expression on some other expressions. So this says, compute a function for me. Tell me which function to apply. Instead of me just saying F, I have some expression here that says compute which function I want to call. Okay, that's what this does. Here it uses the Boolean B to decide, should I call F or should I call G? Okay, that's a more powerful programming technique. Yeah, that's actually considered a very powerful programming technique. What function do I call? It depends. Sometimes that's called dependency injection. The idea is I want to call a function. Which function do I call? Well, it depends. Is the customer a member or is the customer not a member? I might call one function if the customer is a member. I might call another function if the customer is not a member. Does the customer spend a certain amount of money? What function you call in different situations might have to do with. Another example would be I want to sort some list. I want to sort something. Well, am I sorting a list of strings or am I sorting a list of integers? So maybe what I want to call the sort function depends on what I'm sorting. So and that's called polymorphism. If you just say sort something, say sort something, it may actually be that the thing you call has a lot to do with the thing you're sorting. That's referred to as polymorphism. Okay. Now here it's implicit. It'll be done it'll be done by the compiler, but it's still something like this. What's being called needs to be figured out. Okay. That's so there's lots of examples of where the idea of what to call is not just F. It's that what to call needs to be computed somehow. Here, in a case of polymorphism, I would have different sort methods depending on what I'm sorting. So sorting a list of integers would be a different function than sorting a list of strings. Okay. So, and you can come up with other examples where the thing to call needs to be figured out, either at compile time or at runtime. But there's something subtle there, that what you're calling is going to be computed somehow. Here it's just computed real simply. Check that Boolean, either call F or call G. Okay, so that's one idea, that what to call really depends could depend on something. Okay, that was in function application. So there's a deep idea in function application, a new deep idea that what you're applying needs to be computed. Now, function definition, the idea that here was we wanted to separate the name of the function from the definition of the function. Remember, in this notation, which you're used to, you're blurring together that this thing is what the input is. This is what the name is. This is what the result is. This really should be kind of pulled apart and said that F is a name for the function that takes in two inputs and multiplies them like that. Okay, so really the equal sign's in the wrong place. One way to think about it is the equal sign's in the wrong place. The equal sign belonged over here. There's the function, and we call that a lambda expression because it abstractly describes a function independent of its name. So that's the deep idea we want to get at in function definitions. In function applications, the deep idea was you should compute the thing. The function you're going to call needs to be computed. It's not just F anymore. You do some calculation that decides what function to call. The deep idea in function definitions is the function itself should be separated from the name we give it. Okay, and here's a whole bunch. And remember, these were all different notations for lambda expressions. The Java notation, the C++ notation, Alonzo Church's original notation, Haskell's notation. But in all these cases, it's saying F is the name for a function. F is the name for a function. F is the name for a function. They're called lambda expressions because Alonzo Church used the letter lambda on the right-hand side. He used the word lambda, mean I'm beginning the definition of a function. Haskell uses a slash because that's the closest thing on the keyboard to the letter lambda. That's if you think of what lambda looks like, Haskell is actually kind of clever. I think it's kind of cute the way they did that. See the symbol for lambda? If you kind of ignore that part, that's a slash. Okay, so and see AWS lambda, part of AWS is there's a notion of lambda expressions in cloud computing. This is actually real interesting. This is one of the reasons why I want you to learn this stuff. Is modern cloud computing is based on the notion of Amazon. AWS stands for Amazon Web Services. Amazon Web Services, one of their biggest features is AWS Lambda. Okay, there's this notion of lambdas in the cloud. Okay, it's a real modern style of programming. It's called serverless computing platform. Okay, so the symbol is lambda, and it's kind of loosely based on the idea of a lambda expression. You know, it's many steps more sophisticated than this, but it starts with this idea of what we're talking about it starts with this idea of, okay, close these windows. It starts with this idea of a lambda expression. A lambda expression is the function without a name. Okay, it's a function without a name. The function itself is the lambda expression. Okay, so in AWS Lambda, they built a whole cloud platform around this idea. And Haskell took this part of the lambda, which is to them a slash. So there's lambda xy. See, this is lambda xy. So they write slash xy. Okay. Then arrow. This is the input part of the function. Sends it to that output result. Haskell uses an arrow. Java uses an arrow. C++ doesn't use an arrow. They use square brackets to kind of represent the lambda, except it's not really representing the lambda because you can put things inside those square brackets. You can annotate the lambda expression with stuff inside those square brackets. So they're not an empty. It's not an empty thing. You can fill in what goes in those square brackets. But you read it as lambda xy, and there's the output. Alonzo Church used a dot to represent the arrow. Where we use an arrow now in a lot of languages, he put a dot there. So it was lambda x dot, and then on the right side of the dot was the formula for the function, the body of the function. Okay, so our syntax for defining functions wants to have something like, it doesn't want to do this. We could have done this syntax. It would have been easy. There was the example of that syntax. Function f of xy with that result. Okay, so there's function f with parameters x and y, and there's the body of the function. But that's not modern enough. We want to separate. See, this blurs everything together. Okay, so I created a different syntax that said function f of lambda. So now the syntax is function. I'm defining f. F is the name, and lambda is the function. And as I mentioned, in the next language, language 8, these lambda expressions will get to live on their own. In language 7, they don't live on their own. In language 7, they only live inside of the lambda expressions only live inside of the function declaration. So you declare a function as a name and a lambda. And then the lambdas are what actually gets stored inside of the environment. They're the values, but you can't declare them by themselves. You can't just define a lambda expression. Okay. In language 8, you'll be able to define a lambda expression by itself. Now, here's another interesting thing. If we go back to the why we use the apply, okay. Now, here's another way. Think about this. Here's a lambda expression. I'll write it this way. Lambda x times x times x. So there's the cubing function. The cubing function, I didn't give it a name. I could, if I wanted to give it a name, I would say fun cube. That would give it a name. Okay, but by itself, well, it's a function. Not yet in our language, but here's what I want to do. If that's a function, why can't I cube 3? There's the lambda expression, x goes to x cubed applied to 3. This is Lisp. This is written in Lisp, and it's an S expression. But what's interesting, instead of saying a Boolean computes the function, here is the function, but it's a lambda expression. So there's the function to apply. Okay. If I was to use a more C-like notation, I would say, here's Haskell, like lambda x goes to x cubed applied to 3. Okay. F of 3. Okay. So that's a Haskell-like notation there. Or okay, F, there's the function of 3. Here's the Lisp way of writing it. But see, that's an S expression. I'm calling some function. What function am I calling? The lambda of x goes to x cubed. Now, that's not a tree, so we write that in our language, in language 8, this is going to be written apply lambda x goes to x, 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 x cubed, apply the x cubed function to 3. Okay? That's a language, in our case, that's a language 8 tree. Okay? Because we got to translate this list S expression into a tree. So there's a language 8. You can't do this in language 7 yet, but we'll be able to do that in language 8. That's a language 8 tree. Now that's a real legitimate tree. The root is apply, and then its left branch is a lambda expression, and its right branch is 3. So it's going to apply, it's going to call that function directly on 3. Notice the function never gets a name. We know it's the cubing function, but it's not actually named anything here. It's called an anonymous lambda expression. Okay, it's an anonymous lambda expression, an anonymous lambda expression. So in the abstract sense, this is referred to as an anonymous Okay. So I'm calling an anonymous lambda expression. That's kind of like the notation you would be most closely used to. That would be like C or math-like notation. There's the function, that's the f of 3. Here, f of 3. What's f? F is the function that takes in a number and cubes it. Notice that if I change that to that, it's the same function. That doesn't change the function in any way. It's not a function of x or a function of y or a function of z. It's the same function here. It's the function that takes in one number and cubes that number. Okay, so it doesn't matter what I call it. And that's going to be important later on, that this function is not a function of z, it's a function of one thing. I need a symbol for that one thing, so I give it the symbol z here, I gave the symbol x here, but it's really a function of one thing. I have to choose a symbol for that one thing. Notice here, I don't need a symbol for the function name. I'm avoiding the function name. Now in traditional math, f of x is x cubed. Notice that I have, this is immaterial and this is immaterial. If you think about it, what we're really learning is that the name doesn't matter because the function exists without a name. The choice of the parameter doesn't matter, but you got to make some choice. You got to make some choice for the parameter. It doesn't matter if I call it x or z. So I have to have the parameter, but it doesn't matter what choice I make for it. But I don't really have to have the function name. I can really get rid of the function. So notice that we're learning what the abstraction levels are. The function name is really superfluous. Here I don't even have it. The parameter is kind of, it's not superfluous, it needs to be there, but the actual choice of the parameter doesn't matter. And believe me, if you ever teach high school algebra, you'll get students who'll tell you that these are two different functions. They'll tell you, well, one's a function of X and one's a function of Z, so they're different. Yeah, and there actually are programming languages out there where they might be. Yeah, depending on the nature of the programming language, this could be a function of the symbol X. This is a function of the symbol Z. And this is saying if you get the symbol X as input, you replace it with the symbol X times X times X. But if you get the symbol Z as input, you replace it with Z times Z times Z. If you have, there are languages where these two are not the same thing. But see, it depends on the semantics of the language. If the language is a much more abstract kind of language where it's a symbol manipulating language, then X and Y can be thought of as different symbol. X and Z are different symbols. So this function takes in the symbol X and does one thing. This takes in the symbol Z and does another thing. In the kind of programming languages we're working with, and we have to spell this out in the semantics, this variable choice doesn't matter. Like in math, it doesn't matter. That function, those are just two redundant ways of defining F. That's F, that F, and that F are the same F. In all math contexts, those are the same F. But in some strange contexts, they're not the same thing. Okay, so you have to define the precise semantics of what you're working with, whether these guys are the same thing or not the same thing. But in high school math, they are the same thing. And in the notion of a lambda expression, they are the same lambda expression. You know, this, we would turn this into F equals lambda X goes to X times X times X. And this would go to F equal the lambda expression Z goes to Z times Z times Z. And then we'll precisely make the case that these two lambda expressions are the same. That lambda expression is that lambda expression. The choice of the variable does not matter. And then you do that by precisely saying what you mean by a lambda expression. Okay. In a lambda expression, that lambda expression says the same thing that that one does. So this F and this F are names for the same thing. They're not two different functions. Okay. But we have to say that in our language. We have to say what our language is really about. Okay. All right. So this is another example why I want the apply in the language, because I want to be able to apply a lambda expression. But if I apply a lambda expression, that's an S expression, not a tree. Okay. So if I use this symbol, then I'm in the world of S expressions. So notice that the apply, we've seen three reasons now for using apply. It helped with functions of no parameters. It helped with expressions that compute functions. And very deeply, it lets us apply lambda expressions. Okay. It lets us apply a lambda expression without naming it. Okay. And it turns out this and this are just versions of each other. Okay. We're eventually, this is just saying apply the value of this expression to that input. Apply the value of this expression to that input. The value of this expression is a function. The value of this expression, well, you have to compute it. It's an if expression. So you compute the if expression, and then it returns either an F or a G, and it better be the case that F is a function and G is a function, like they are here. Okay. So assuming that F is a function and G is a function, then this if expression will give you back like I could put a lambda expression right there, and I could put a lambda expression right there. So then this if is choosing between two lambda expressions. See, that would just be a more sophisticated version of this. Instead of having a lambda expression there, I could choose between two lambda expressions. Or I could put the names, or I could put a lambda expression there and a named function there. Okay. But I want to say apply the result of computing this expression to here. Now, In language 7, we can do this, but we won't be able to do this until we get to language 8. Okay, lambdas are not things by themselves yet, because when you make a lambda a thing by itself, there's some technical issues that you have to worry about that make things much trickier. So lambdas are not standalone functions yet. Lambdas right now in language 7 only exist as the right-hand side of a function definition. They only exist as function, name, lambda expression. So that we have we're using lambda expressions in a really restricted way so far, but we're opening up the idea to using these lambda expressions as independent entities on their own. So we're opening up the window to this idea, but not yet. So it's an idea. So language 7 lets us do this, okay, but language 8 will let us do this. And that's deep programming right there. Okay, that's pretty deep programming, and we'll see, what is needed extra to make this work that language 7 doesn't do. Because this stuff here, like I said, this can be done in C. Remember that's probably valid C right there. Okay, so this idea of, well, evaluate this expression and either F or G names a function. Okay, so but they name a function. That's the C idea. F or G name a function. Here, this guy is a function. That's the deeper idea. In language 8, this will say apply this thing which is the function. Okay, in languages like C, what you're really saying is, well, you can choose between these two names. That's a name. That has to be a name. F has to be a name, a pointer to a function. That has to be a name or a pointer to a function. You can choose between two pointers to function. You can't choose between two functions. You can't put a function definition there. You can't put a function definition there, not in C, not in Java. Well, you can't. Well, in modern C++ you can, because modern C++ has lambda expressions. Okay, so in modern C++ you can put a function there, a lambda expression. And in modern Java, you can put a function there, a lambda expression, but not in traditional C, well, not in C. So in modern C++, you can put a lambda expression there. Traditional C++, no, and in C, there are no lambda expressions. Okay. But C++ and Java took years and years and years to get to where they could do this stuff with lambda expressions. Okay. All right. So we've got two syntaxes, but why I'm beating it to death is those two syntaxes each introduce a real deep idea. The apply is there because this should be something that returns a function. If it was simply name of function parameters, I wouldn't need apply, but I wouldn't have a very sophisticated language. Okay, so the key here is this: I'm trying to do something more sophisticated. This is an expression that returns a function. And then again, over here, if I was just saying, I could easily make the language look like this. There. Okay, then I don't even need that. Okay, but fine. That's an easy language to define. Function of a variable. Function named this with this parameters and this body. Okay, that would be, but there's nothing deep there. See, that's being very old-fashioned, C-like, Java, old-fashioned Java-like. So it's not opening up the idea of a new language construction. It's not letting you see that there's something deep involved there. It's just traditionally saying, oh, I'm declaring a function. Here's its name. Here's the list of its parameters. And then here's the body, the function. By doing it this way, we're saying, well, what we're really saying is that the function has a name and a lambda expression. The lambda expression encapsulates the idea of function, independent of name. A function is something that takes in parameters and gives you back a result. A function a lambda, takes in parameters, and gives you back a result. So we've abstracted the notion of function away from just the idea of naming the function. Okay, so this syntax leads us in a more modern abstract direction. Separate name from what it does. Okay, and then you get these things like over here, you get, well, the things we did the other day. The name is abstracted away from what it does. Okay, and there's all the different syntaxes for abstracting the name from what it does. Okay, now let's look at, oh, and I can't overemphasize how important in modern computing these ideas are. If AWS is going to name their modern cloud system Lambda, that gives you a sense of how deep they think these ideas are. You know, Amazon has become one of the richest. They probably make as much or more money from this as they make from selling underwear and books and cleaning. Amazon actually makes, I think it's half its income from their cloud services, and the other half is from selling stuff. Yeah, their cloud services are phenomenally profitable. You know, this AWS Lambda makes a ton of money for them. They're selling Lambda expressions. Yeah, Lambda expressions are computations. They're selling a way of doing computations. They'll they'll house your computations on their servers, and this is their abstraction for saying, you tell us what the computation is and we'll do it for you. You tell us what the lambda is. The lambda is the thing that represents a computation. See, the lambda represents a computation. Doesn't need to be named really, but they will give them names because they're hard to identify without names. But the key is the calculation. So they call it Amazon Web Services Lambda. It's one piece of their web services, the Lambda part, what they call the serverless computing platform. Okay, yeah, and they gave this cute name. They chose the name wisely. They knew that it's really based on this idea of lambda expressions from functional programming. There's 3 cloud platforms out there: Amazon's, Microsoft's, and Google's, and they all 3 have something like this. And Microsoft just calls them Author functions. Okay, they don't use the lambda expression in it, so they just call it Author functions. Again, this is this event-driven serverless computing. Notice that that's the same phrase that they're using, the event-driven serverless computing platform. Okay, Author Lambda, well, AWS Lambda, Author functions. They might actually say somewhere down here that they're kind of like lambda expressions. I don't know if this was meant to be a funny looking lambda over here, and Google too. Google has something like this. Google Cloud Platform is the name of the system. And then there would be their lambdas. Cloud functions. Notice I Google the phrase lambda and I get their cloud functions. Okay. Functions as a service. That's the other phrase people use for this. FAAS, functions as a service. Okay. Amazon got there first and they coined the lambda expression. Yeah, AWS Lambda. So they gave it the fancy name. And then Microsoft calls them Author functions and Google just calls them cloud functions. Okay. And yeah, it isn't this in an immediate sense, but it's motivated by this. It's motivated by understanding how, we want to separate what a function does from its name, and we want to call these functions in interesting ways. We want to do interesting things with functions that more than what you just do in a language like C or C++ or old-fashioned Java. Okay, so there's there's lots of ways these ideas are entering modern computing. Lambda expressions are just becoming ubiquitous in modern computing in so many ways. Okay, so learning what people mean by a lambda expression is a really good thing to do. Okay, all right, now let's look at actually implementing these guys in our language. Okay, so they're actually implemented in the evaluator. Okay, okay, there's two things to look at. How do we handle this, and how do we handle this? Okay, this is just building a tree. The way you handle a function is you build a tree that represents the name of the function and its lambda expression. And its lambda expression is a tree that represents the list of parameters and the body of the function. Okay, so the simplest thing to do is to think of it as a couple of examples. So here's a simple program in language 7, and I'll just make up an example. So I'll say, I have a function, f, lambda, x, and the function will be the squaring function. Okay. And then I'll have another function, g, and that'll be a lambda. And I'll let this function take in 2 parameters. And it'll be the adding function. It'll just add the 2 parameters. Okay, and then there's the rest of the program. Okay, so the abstract syntax tree for this, which is first we want to decide what does this stuff build? What tree does this stuff build? Because that's essentially all the fun does is build a tree. It just builds the tree. Okay, it's going to be apply where the real work goes. Okay, so apply is where the real work is. Okay, so fun will just be, okay, prog will have a left branch, which is a fun, and it'll have a right branch, so far only, a right branch, which is another fun. Okay, now the left branch fun is an f and a lambda, and the right branch fun is a g and a lambda. Okay, so there's the f and there's the lambda. Okay, and then here's going to be the, see, can I move this over a little bit? Okay, there's the g, and g's got its own lambda. Okay, and then under the lambda is going to be the parameter. This one will be the parameter, and then the body of the lambda. The parameter is x, and the body is a product of x with x. Okay, and over here, the g has this lambda, and this lambda's got a parameter a parameter b, and then a body. So it's got a parameter a parameter b, and then a body, which is a sum with, a sum of a and b. Okay, so that's all the first thing does. Fun just builds that tree like that for us. That's the key. That's all it's really, its only real job is to be parsed into that tree. At runtime, it really doesn't do anything. It really doesn't do much of anything. So let's look at the code for, okay, so now the parser actually, the parser builds this tree for us, not at runtime. The question is, what happens at runtime when you hit this fun? Okay, So the parser builds this tree for us. What happens when at runtime, when I hit fun? And the answer is it really should put in the environment. So here's the global environment. Remember, the global environment holds variables. Okay, so what we're really doing is we're putting an F variable in the global environment and a G variable in the global environment. So at runtime, the parser builds those trees. The evaluator walks the tree. So the evaluator walks the tree and sees fun. When it sees fun, it says F goes into the environment, and then it puts this lambda expression as its value in the, actually, that's what it really does. We'll see when we run it. It actually says the global environment holds F function pointer at this lambda expression. If you want, you can think of functions as pointers, just like they are in C. This thing points at that code. Okay, and then now it doesn't walk the lambda expression. It puts into the environment F pointing at that lambda expression. Then when it sees this guy, it puts G pointing at this other lambda expression. Okay, so it builds that environment. Okay, now if the function, if the next line of code was there, cat 5, that creates a variable that would create another thing in the environment that would be a variable cat with the value 5. Okay, yeah, and if there was another line of code, see, the var fun puts a function definition into the environment, var puts a variable declaration to the environment. There's not much difference between them. Funs have lambda values, vars have, for example, I could have var dog true. That's just a Boolean value. Okay, so that would put into the environment a variable called dog with the value true. So now I would have 4 variables in the global environment: a variable called f, which names a lambda, a variable called g, which names a lambda, a variable called cat, which names the number 5. Yeah, and here this would have a tag. If I do this more carefully, this is a lambda with the tag. I forget what I called it. Oh, value L, value B, value I. Those were the. Oh, I'm sorry. Well, the tag is int tag, bool tag, lambda tag. Okay, so this guy would actually be int tag 5. This one would actually be bool tag true. Okay, and these would be values with lambda tags. So that'd be a lambda tag. Is that how I spelled it? So I have a lambda tag. So this one's a lambda tag. And this one also is it's in the environment as something with a lambda tag. Okay. So I would have these guys in my environment. I'd have two values with lambda tags, a value with an int tag, and a value with a bool tag. Okay. So put something in the environment, put something in the environment, put something in the environment, put something in the environment. Okay. Then eventually I want to get to apply f to, say, 4. Okay. So let's start. So now let's just look real quickly at the code for putting this guy in the environment. Okay. Okay. So you go here and you need to when you evaluate a prog, as we see here, evaluate a prog can either find funds or vars. See, the prog can start with funds or vars. So you go here, you evaluate prog, and it checks, well, it checks that the first element is prog, which, remember, a program can just be one single expression. If you look at the grammar real carefully, a program can either be, where is it? A program is either a single expression or a prog. See, a program's either one expression by itself, like add 3 to 4. That would be a real simple program, add 3 to 4. So a program can be either a single expression or a prog, which groups a bunch of expressions together. So evaluate prog first checks to see if you have a prog branch. If you don't have a prog branch, it just evaluates one expression. Okay. If you do have a prog branch, then you have a bunch of you have a bunch of fun or var expressions followed by the body of the program. So you have a bunch of function definitions or variable definitions, function definition or variable definition, followed by the body of the program. So here you have a loop that loops through all but the last branch of the tree, checks if you have a function definition, then that's handled differently than arbitrary definition. So here's the thing, handle fun is the thing that basically handles the putting a function definition into the global environment. Okay, so if you have a function definition, I wrote it as a separate function, handle fun. Okay, here's handle fun. Okay, so what does handle fun need to do? Handle fun needs to look over here. There better be a variable name there. So it looks on the left branch and looks for a single variable name. Okay, so it gets the left tree and it checks that it's a variable name. Okay, see, it checks that it's a proper variable name. Something that begins with a letter and is a string of letters and numbers. Okay, so it gets the left branch, the 0 branch, and makes sure it's really a name. Okay, so that's the first thing you do. Check that this is really a name. Check that this is really a name. Okay, then after it's done that, it looks to see if there should only be 2 branches. Okay. Oh, I forgot. Yeah, I should even have a runtime check in front of this one to say that the handle fun should have exactly 2 branches. Okay, because a fun, if you look at the grammar, a fun has exactly 1, 2 branches. It's got a single variable name followed by a lambda expression. Okay, so I could have started this off with, if the degree isn't 2, that there's a problem. Okay, but after it checks that there's a valid variable name, the next thing to do, actually before going to that, what it does is you cannot redefine a function. That's a syntax error. Most languages don't let you redefine a function. Okay, so if the function already exists, that's an error. That's a runtime error. So after it checks that it's a variable name, it checks if it's defined. If it's defined, throw an error. Okay. All right. All right. So step 1, make sure you have a real name. Step 2, make sure it's not already been defined. Step 3 is make sure this right-hand thing is a lambda. Okay. So step 1, check that it's a real name. Step 2, make sure it's not defined. Step 3, check that the next branch is a lambda expression. Okay. Check that the next branch is a lambda expression. Actually, I should probably number these. I mean, this is step 1. Okay. Check that we have a proper name. This would be step 2. check the name hasn't been defined. This would be step 3. Okay, now check that the definition, check that it's really a lambda. So check this as a proper variable name, check that it hasn't been already defined, check that there's really a lambda over here. Okay, if there really is a lambda over here, then we need to put something in the environment. See, then we're ready to put something in the environment. That's the last thing we'll do. So, okay, this is step 4. Put it in the environment. Okay, add it to the environment. I mean, there's this intermediate step of getting a pointer to the lambda. Okay, but that's not a big deal. What it does is it makes it into a valid value that you can put into the environment. So if you want, you can think of this as a step 4, create a lambda value. So create a function value, then put the function value in the environment. Okay, so create that lambda value with the lambda tag, then add it to the environment. So check that there's a variable name, step 1. Step 2, check that it's not already been defined. Step 3, check there's really a lambda. Step 4, build this environment, build this value object. Step 5, put it in the environment. Okay, so there's the 5. So that's how you handle a lambda expression. Okay, that's how you handle this part of the language. So then next on Wednesday, we'll talk about the real heart of the matter, apply. The real deep thing, the apply. How do you actually call a function? Okay, that's what we want to really, that's the thing that we're building up to. So what we did today was we talked about the abstract idea, like why do we make a big deal of the lambda expression? Why do we make apply so that we can do, why do we just not have that? Why do we have apply so we could do more abstract things? So, we're introducing an abstract idea here. We're introducing an abstract idea here. The abstract idea here is separate function from its value. The abstract idea here is this guy doesn't have to just be a function name. This can be an arbitrary expression that computes a function. So you apply the result of some calculation to a function. Remember, apply the result of a calculation to a parameter. And the result of this calculation should be a lambda. Okay, so we want to, here we're going to start with the trivial case, but eventually we'll see that it's really more sophisticated than that. So we could put an if expression in there. Yeah, and we want that if expression to return a function to us. Okay. All right, so we'll quit there. So we're ready now to talk about what apply does. Okay, so we've beaten to death what lambda expressions are. We've beaten to death what apply means, how it's written. We've seen what this does in the building something in the environment. And then the last thing to do is, what does apply really do? Yeah, how do you call a function? What do you do when you call a function? Okay, anybody got any questions? Okay, your homework assignment that you're working on is related to this in the sense that you're putting something in an environment. So you're supposed to be kind of getting a sense of how the language works with the environment. You're doing it in the case of a for loop. You're building an environment to handle the for loop. Okay, so that's a little example of the kind of things we need to think about. So that's a case of something where you have to think about, I need to build an environment to hold a local variable, the for loop variable. Okay, so that helps you think about these ideas here. Okay, all right. So okay. So any question? If you have a question about the homework, either come to office hours tomorrow or send me an email. Okay. And then we'll go ahead and quit. So we'll meet again on Wednesday, and on Wednesday, like I said, we're going to say, what does apply really do? Okay, and then after that, we're ready to start the next language, language 8, which Well, actually, after that, we'll look at all these examples. There's lots of clever examples in this folder of language. Language 7 is a real programming language. Here's the GCD program written in language 7. There's the program for computing GCDs, greatest common divisors. Yeah, you can compute Fibonacci numbers, you can compute factorial, you can do all kinds of things in this language. Here's the mod function, the modular calculate function, and then here's the GCD function using the modular function. Okay, so define mod, define GCD. Here's calculating a bunch of GCDs. Yeah, and yeah, you can actually write real code in this language. It's about the level of this of it's a baby version. It's like visual. It's like basic. Yeah, like language 7 is about the power of basic. Okay, so after we look at how to do apply, we'll look at some of these examples of what language 7 can do, what kind of programming language it really is, and then we'll start language 8, which is a functional programming language. That's the real goal, get a real functional programming language. Okay, so we'll quit there and we'll meet again on Wednesday and do applies. Okay, and I need to find the button for, okay, so see you on Wednesday. Bye.